Hello, this is How to Save Humanity in 17 Goals, a podcast brought to you by Nature Careers in partnership with Nature Sustainability. I am Monica Contestabile, Chief Editor in Nature Sustainability. This is the series where we meet the researchers working towards the Sustainable Development Goals agreed by the United Nations and world leaders in 2015. Since then, in a huge global effort, thousands of academics have been using those targets to tackle the biggest problems that the planet faces today. Each episode ends with a sponsored slot from La Trobe Institute for Sustainable Agriculture and Food in Melbourne, Australia, where we hear about how its researchers are focusing on the SDGs. In this episode, we look at Sustainable Development Goal number 15, to protect, restore and promote sustainable use of terrestrial ecosystems, and meet an Indonesian researcher who works to conserve tropical peatlands and mangroves.
Hello, my name is Sigit Sasmito. I'm from Indonesia, but currently based in James Cook University in Australia, located in the northeast Australia near Brisbane. I'm currently working on the ecosystem restoration, especially on the coastal wetlands restoration across North Queensland and also across Southeast Asia, especially on the peatland and mangrove ecosystems in Southeast Asia and globally. So the Sustainable Development Goal number 15 by definition is to protect, restore and promote the sustainable use of terrestrial ecosystems and sustainably manage forests, combat desertification, and halt and reverse land degradation and halt biodiversity loss, right? And my research is directly linked with those goals, especially on the wetland restoration and conservation that really can contribute to the SDGs 15. But also not only for the SDG 15, there are some other goals that my research can contribute, especially SDG 13 on the climate action and also SDG 14 on the life below the water. Peatlands are general lands. It's built up from the accumulated organic matter and is mostly associated with the freshwater wetlands. Well, the mangroves can be categorized as shrubs or forests distributed across the tropical and subtropical coastal areas. So mangroves are located in the saline waters, but the peatlands mostly located in the freshwater wetlands. But some areas in the tropicals, like in Indonesia or even Malaysia, there are some areas that both peatlands and mangroves are overlapped. So that's really good and really unique because both ecosystems coexisting together. We have peatlands underneath in the soils, peat soils, but above the peat soils we have the mangroves. So actually mangroves contribute to the organic matter accumulation. Why peatlands are important is because of the high carbon stocks, and it's due to the low decomposition rates in both ecosystem in peatlands, mangroves, because in the mangroves and peatlands they are inundated because it's wetlands, so that's why the decomposition rate is very low, and then the organic matter keep accumulating over millennia. So that's why the amount of the carbon density, especially carbon stocks per area, is very, very high. I grew up in the rural area of Eastern Java in Indonesia. So I completed my bachelor degree in IBB University at the time. And then I got the first job in the Center for International Forestry Research in Bogor. So first job, I had the chance at the time to join a big research projects on the global survey of the carbon in the wetlands. So I started the journey of the research about mangroves, about peatlands, and especially to assess their carbon stocks across all islands in Indonesia and also some other countries. I pursued my dream as a researcher because this kind of work is not very popular, especially in the developing countries like Indonesia. And then I continued to pursue my PhD in Australia, looking at the impacts of the land use change on the carbon emissions on the mangroves in Indonesia and also at globally. So that's the journey I have so far. Why it's important to conserve peatlands and the mangroves? Because mangroves and peatlands a high amount of the carbon stocks per unit area. If compared with the other types of the forest, it can be 3 to 10 times more carbon stocks compared to those forests. So that's why if we lose small amount of the tropical peatlands or even mangroves, it's comparable if we're losing a high area of the tropical forest, for example, because the carbon density are higher. So that's why if we conserve peatlands and mangroves and restore the degraded peatlands and the mangroves, it can be useful or cost efficient to tackle the climate change at the national or even the global scale. So currently Indonesia aims to restore 1.2 million hectare peatlands and 600,000 hectare of the mangroves. We know that this is very ambitious targets for any ecosystem restoration. However, I think this is a good initiative and I think it's moving in a good direction, especially since there is a big opportunity to include these ecosystem restoration programs to achieve the global agendas, including the Paris Agreement and also multiple sustainable development goals. What are the drivers of the degradation? In this case, the peatlands is mostly due to the industrial agriculture. And one of the characteristics of the degraded peatlands are drained peatlands. So to restore the drained peatlands, there are some approaches. The first one is the rewetting approaches, where the projects have to raise the water table, at least at the similar level to the natural states. So by raising the water table, at least the peatland system, the drain peatland system will reduce the CO2 emissions coming from the soils. However, our research also shows that raising water tables might also increase the methane emissions. And the second approach is the revegetation. So basically, vegetations can be, for example, like planting native species, planting trees on the degraded peatlands, and of course, the aim is make the peat swamp forest recovery, but the time to take vegetation or peat swamp forest require a long time to recover. I think the barriers of restoring peatland and the mangrove ecosystems, there are a lot of factors that need to be considered to determine the best location for restoration. For example, this is the case for the mangroves restoration in Indonesia. We have to make sure who own the lands and maybe the sites having a higher value to be used for other uses compared to the restoration. So I think this is really the main barrier as well. And the second barrier is also about the ecological suitability. It means that if the restoration project is not suitable in the mangrove areas, for some of the projects that we know, they just do planting mangroves on the seagrass habitats and sometimes on the mudflat habitats, and those habitats are not suitable for mangroves, and of course the mangroves will die and failure is common if we do this kind of approach. And then what is the current land cover conditions? What is the current land cover condition is really important, because that can be aquaculture, that can be other agriculture, that can be settlement. Used to be mangroves there, but you have to really see first what the current land cover condition before restoration approach. And then further barrier, I think this is the most common as well, is having low monitoring investment in the restoration programs or restoration projects. We know that a lot of efforts on mangrove planting just happen in the one time, but without further follow-up or monitoring or evaluation. So that's really important. So Indonesia has really ambitious efforts in terms of fulfilling the ecosystems or ecosystem restoration, especially for peatlands and the mangroves ecosystems, because also Indonesia has the largest area of the mangroves in the world and also one of the largest area of tropical peatlands especially. So that's why Indonesia has a huge target of the restoration for both ecosystems. Obviously, by having these ambitious targets, Indonesia has become the leader of this effort, especially in the ecosystem restoration, right? We know that although sometimes having ambitious target is important, but it is also way more important to understand how well these restoration targets can be successfully achieved. So I think this is where science can contribute and play a key role in closing these gaps and challenges. So I think improving evidence-based practice in policy making based on the localized evidence for any countries, it's really important. So it's not necessarily the approach in Indonesia that can be adopted in other countries because they have different characteristics of the geographical conditions. By using peatlands and the mangrove restoration as a study case or example, I think the achievable of the SDG, especially SDG 15 on the restoration of the terrestrial ecosystems, will really depend on the various factors, right? Including whether restoration targets are defined by evidence-based policy practice or not. That's really important. And the more important is that if the implementation of the restoration is conducted by using the careful planning, implementation, and also monitoring programs. So I think that's really matters to achieve the SDGs in just 6 years from now. And in the end, all of these efforts must involve local communities and have to be providing benefits from the local communities because their livelihoods is really depending on this preservation and conservation of this unique ecosystem, especially on the peatlands and the mangroves.
Thanks for listening to this series, How to Save Humanity in 17 Goals. Join us again next time when we look at Sustainable Development Goal number 16 to promote peaceful and inclusive societies and access to justice for all. But before we do, next up, we'll hear our researchers at La Trobe Institute for Sustainable Agriculture and Food in Melbourne, Australia, the sponsor of this series, are working towards the targets set by the UN.
I'm Karis Bazaka, and welcome to this podcast series from the La Trobe Institute for Sustainable Agriculture and Food at La Trobe University in Australia. I would like to start by acknowledging the traditional custodians of the lands where La Trobe University campuses are located in Australia, and to pay respect to Aboriginal and Torres Strait Islander cultures, as well as to elders past, present, and emerging. Across this 6-episode series, you will hear from academics at the top of their fields as they discuss groundbreaking research happening at the La Trobe Institute for Sustainable Agriculture and Food, also known as LISAF. Through LISAF, La Trobe has developed a holistic approach to food security, and this paddock-to-gut philosophy is delivering innovative research and significant academic and industry partnerships across the entire value chain. Its success so far can already be seen in the Times Higher Education Impact Rankings, which measure university performance against the United Nations 17 Sustainable Development Goals, or SDGs. In 2024, La Trobe was ranked first in Australia and 5th globally for SDG 2, Zero Hunger. Now stay tuned to hear firsthand about the research of LISAF as it delivers innovative solutions for sustainable and nutritious food production in a resource and climate-constrained world.
Just in Australia, we're spending something like $2 billion each year on nitrogen fertiliser. So if we can reliably deliver more biologically fixed nitrogen to our agricultural systems, then we could boost the profitability of legumes, but also help to reduce the nitrogen fertiliser budgets on the bigger crops like wheat and barley that we're growing.
That is Dr. Dougal Reid, a plant molecular biologist and lecturer in plant science at La Trobe University, whose primary focus is on symbiotic nitrogen fixation in legumes, a family of plants that include the common crops beans, chickpeas and lentils. Dr. Reid is also a research group leader at LISAF, who, along with a team of international scientists, made a significant discovery that was published in June 2024 in the international journal Nature.
One of the key characteristics of legumes is their ability to obtain nitrogen from a symbiotic relationship with bacteria that are hosted in the roots of the plants. And this means that legumes can sustain their growth with biologically fixed nitrogen as opposed to requiring nitrogen fertilizer. Aside from the size of the plant, the main determinant of how much nitrogen legumes fix is the level of nitrogen that's already in the soil. And this is because legumes evolved to switch off the process to save energy when they don't need it or when nitrogen's already freely available in the soil. But what we identified is one of the switches that controls this shutdown process. And we found that if you remove this switch in a genetic sense, the legume plant no longer switches off the process and they'll keep getting more and more nitrogen from the bacteria in the roots as opposed to obtaining it or depleting the soil nitrogen. The result of removing this switch is that the legumes in a crop rotation, they might leave more nitrogen behind after they're harvested. So that could flow through to benefits for the cereal crops that are grown in the next year through lower needs for nitrogen fertilizer. There's also some evidence that increased nitrogen fixation can also benefit the legume itself through higher protein levels in the seed or even increased yields.
The genetic regulator the team uncovered is known as fixation under nitrate, or FUN, and its discovery was the result of a long collaborative effort by scientists around the world to screen for genes related to nitrogen fixation in legumes.
This project actually started when I was in Denmark at Aarhus University. For a long time, the research groups there have been led by Jens Stoggaard, a visionary leader in legume genetics. They've worked on really developing genetic resources in legumes, which was really what we needed to be able to do the screen. I had a postdoc called Jishun Lin who joined us there and was keen to do another screen where we take a big population of plants and try to find interesting mutants. He really drove the discovery phase, screening probably in the end 150,000 or so plants to find the interesting mutants. And then once we found the gene that we wanted to focus on, we had a really great collaboration with the biochemistry and structural biology group there, which was led by Casper Andersen. So I think quite diverse expertise was able to help us go from that original genetic screen right through to identifying some of the mechanisms that are at play and how this switch is regulated in the plant.
Dr. Reid says there are multiple benefits to working within an international team on this type of project.
One, of course, is gaining the experience and capability in key areas. So people that have already developed particular model systems or research skills, so leveraging those existing skills to be able to innovate quickly and efficiently in a big project is key. People doing what they're already good at can save on a lot of resource development. But also I think science is done a bit differently in different countries. So funding from national bodies tends to be framed in the priorities of that country. So maybe the emphasis is placed on different areas. So by bringing together teams internationally, then you can develop on the strengths from each of those countries.
The team is also part of the ENSA project, which stands for Enabling Nutrient Symbioses in Agriculture. It's funded by Bill and Melinda Gates Agricultural Innovations, a non-profit organisation also known as Gates Ag One. The company invests in breakthrough agricultural research to meet the critical needs of smallholder farmers in sub-Saharan Africa and South Asia.
This project's been running for a bit over 10 years now, and it's really working to try and translate the findings of this particular work into crops that are relevant for smallholder farmers, in particular cowpea and soybean. But more generally in the project, we're interested in how we can increase the benefit of symbiotic relationships between plants and microbes, such as arbuscular mycorrhizal fungi, which is a really important way of plants acquiring nutrients, as well as, of course, biological nitrogen fixation. So those are really the key aims within that project.
This work with ENSA and its benefits to smallholder farmers also ties in with La Trobe's focus on the SDGs, particularly SDG 2, Zero Hunger, which is about ensuring food security and the promotion of sustainable agriculture.
That's how I see cowpea really as a key target for us, because it's one of the really important crops for smallholder farmers, particularly in sub-Saharan Africa.
With the discovery of the genetic off switch, there's a clear path ahead for the team.
We did our initial screen in a model legume, but this is not something that people are eating or that is really a important grain legume crop. The key thing now is to try and translate it, develop a proof of concept, and to establish in crops like cowpea, soybean, but also in faba bean, which is a really important crop in Europe and here in the higher rainfall areas of southern Australia.
Another focus is on the mechanics for GM, or genetically modified crops. This means understanding biologically how the switch is being regulated within the plant so the team can make targeted changes.
So if we understand how the switch is activated or deactivated, then we might be able to go in and make a specific change within that protein. That's especially relevant for legume crops. There might be enough resources to develop genetically engineered crops in wheat or soybean or maize, for example. In Australia, we have at least 6 major pulse crops, and that's a much smaller market in percentage terms. So being able to really efficiently create innovative new varieties that we can implement without the really resource intensive and costly regulation associated with GM, I think is important. So having that mechanistic understanding can help us develop those more efficiently.
Moving into this uncharted territory has its challenges.
The first one really is to demonstrate that there's a benefit of this type of characteristic in a legume crop. All the work we've done so far in terms of this nitrogen fixation regulator is looking in model species. But once we go to the field and we look at multiple environments and try to understand whether that has an impact on yield or performance in the field, I think that's the real key challenge going forward. It's also possible that we tune the switch a little bit too much or too little. And if you turn it too far one way, then we might detrimentally impact yields. So it's really about finding the right balance.
Dr. Reid hopes to see this research having real-world impact on both an Australian and a global level.
I really hope that this kind of work can make it into farmers' fields in the end and achieve the full potential of reducing nitrogen fertiliser use, increasing the uptake of legumes in our cropping system and the benefits that can come from that. In Australia, that's really going to be in our major pulse crops, making them more appealing to farmers and helping reduce our nitrogen requirements in those major crop rotations. Internationally, of course, my main focus is really on cowpea at this stage. Something like 90% of the world's cowpea is grown in Africa, and it's an important protein for more than 200 million people. So if we can lift incomes for some of those smallholder farmers by reducing their input costs or maybe increasing yields, that would be something that we could be really proud of from a research perspective.
That was Dr. Dougal Reid, a plant molecular biologist and lecturer in plant science at La Trobe University. You can read the paper Dr. Reid and the team authored by visiting doi.org/NCR7. Join us for the next episode in this series, in which we'll explore the research of the LISAF Centre for Food Science and its potential economic and health outcomes.